All right, so let's look at the plan for this and next week. This week seems to be super short, right? Got 2 exams and 1 break on Monday. It's already the last day of the week. So we'll run the problems, the main issues on the midterm exam really quick. Not too many major issues, but I will go through that probably, maybe spend like 5 to 10 minutes to go through all the problems, maybe longer. And then we'll go through the SAR ADC's algorithm, so can prepare you guys for the quiz on Monday next week. You guys are like, oh, not today. If I knew that, I won't come. All right. The register circuits for the SAR ADC, D flip-flops, and you can see in the past we used to do the ADC's circuit in LT Spice. Then we moved to electric VLSI for 1 semester. So this semester I want to do everything in cadence. So if you look at the schematic, it looks like this. So now we are at this circuit, which is a major core algorithm circuit of the ADC. It's a SAR logic. We already know how to build a R2R DAC, right? So the resistor strings. So these are just D flip-flops. I'm going to cover all different types of D flip-flop for you guys. Comparator, there's a certain circuit for comparator, probably 2 or 3 different types. And we'll pick up one of them because you have a wide swing from rail to rail. So we'll pick up that one. And timing are basically just counters. And you need to build a counter using D flip-flops. And we're going to cover D flip-flops next week. So I didn't get a chance to post the D flip-flop assignment for next week, but I'll do that after this lecture. Okay. So I'm going to ask you guys to build that D flip-flop in electrical VLSI, including schematic and layout and simulation. So I will show you the detail of the circuit hopefully later today. And come back here. Sample whole circuit is a totally different circuit compared to other ones. It has capacitors, has charge pumps. So in order to understand what's really going on over here, you need to understand first the charge pumps and second bootstrapped circuits. So these will be covered the week after next, okay? So we'll go through all the details of the circuits. Then eventually, you guys will be very confident in designing this ADC circuit. And then we'll let you guys go through cadence tutorials. So we'll build everything in cadence as a course project, including layouts, right? So these are the details of the circuit, a schematic in LT Spice that I did last time. So we'll probably spend like 2 weeks to cover the theory behind the scene, right? So let's do this first. I know this could be boring for some of you guys. I mean, the average score is probably lower 80s, 78, 79, I estimate. And we got 1 or 2 people in the 90s and a bunch in lower 70s and 60s. Right? Do this really quick. The first one, you can see the problems are really easy. But the only issues are just so many traps. And so it won't take you too much time to get it done, but it's not that easy to get everything right. So if you look at this one, what's the period of the square wave? Easy, right? 2 microseconds. And I think a lot of you guys over-prepared. Just over-prepared. Because I put that on the notes, this is the delay for the wave. And you directly put a 5 nanoseconds or this is delay, right? The starting voltage and high voltage and time delay. That's what I put on the notes, right? And a lot of you guys just put a 0 as the time delay, 0 seconds as the time delay, and which is wrong. So 0 means what? The time delay of the input. So whenever you start a simulation, it takes 0 seconds to run the whole series of the pulse function. There's nothing to do with the circuit, just the input. That make sense? It's just the input, just the voltage source. It's a time delay internally inside the pulse function, but there's nothing to do with the external circuits. And we went through several different quizzes and homework assignments on this, right? And you don't need to derive anything. Derivation is not required. So directly just write down TD equals 0.7 RC. And if you just look at the units and also find out a lot of guys are not really familiar with the units. Is that symptom from the high school? High school teacher didn't cover units really well. That's why no. Okay, let's blame the calculus teachers here, all right? So pico is what? Pico. Negative 12, right? And nano is negative 9. And so probably, it's astounding. And almost 50% of guys are making mistakes on the units. So 1K, 0.7 times, that's K, right? This is pico, and eventually you're getting 0.7 nanoseconds. So you can get full points just by writing this down, okay? Super simple. And for this one, what is the resolution of the DAC? I got all different types of answers. I think I stressed on this the first day I introduced DAC. So during the interview, when people ask you, what's the resolution of the DAC you used for your senior project? So what's the resolution of the ADC you used for your senior project? And you don't want to talk about anything else. Just want to tell them it's a 10-bit, 8-bit, or 12 bits. Right? That's it. That's the only answer you want to tell them. So for this one, how many bits? 3. So it's a 3-bit DAC, and that's the resolution. Okay? Definitely, you can understand the resolution by the smallest voltage it can resolve. Definitely, it is a resolution. Sometimes we say, hey, the ADC or DAC can resolve up to 1.2 millivolts, which makes sense. But whenever people talk about resolution in general for a DAC or ADC or any type of data converters, and usually they're talking about how many bits are there in the system. Keep in mind. So you guys are electrical engineers, so make sure you guys are answering the question in a professional way. So how many bits? This is a 3-bit DAC. What is the digital input of the DAC? It's a really simple question, but test that if you understand this one deeply, right? So what's really going on? Which is MSB, which is LSB? We went through the Stefan's equivalent circuit and superposition for so many times. But eventually, did you really summarize by yourself at home when you're looking at this circuit? Oh, this is one is MSB, this is LSB, right? Did you realize that? So the reason for that is whenever you give a 1 here, is actually 50% of the whole range. So which means the 1 here means what? How many voltage? 2.5, right? Okay? And this one is 0.25. No, sorry, 1.25. So eventually the digital input will be 110, not 011, because 011 will be 3, 110 will be 6. So this should be 6, not 3. See how simple these answers are. So 3, what is the analog output? Analog output, 5 volts divided by what? 2 to the third times 110, which is 6. So eventually you are getting 5 volts divided by 8 times 6. And you are getting 15/4, okay, or 3.75 volts. You can also directly write down the weights of every digital input. So this one is giving you what? 2.5 volts. This one is giving you what? 1.25 volts. And eventually V out analog wise equals 2.5 volts plus 1.25 volts, which is 3.75 volts. Either way, you get a full point. Probably only 2 to 3 of you guys get everything correct over here. Cross-section views. Cross-sectional views. So for the first one, nothing fancy here. It's basically just 3 metal pieces. We got Fox, Why Fox? Because there's no P select. Why? Because P active. Because P active will open up a window on Fox, right? So eventually expose that P substrate to all the diffusion. But because you don't have a P active, so Fox should be intact. Do you have poly? There's a poly layer, but you don't have anything in the poly. Do you have metal 1? Yes. 1, 2, 3. Metal 2, nothing in there. Metal 3, nothing in there. I just labeled them, okay? Fox, poly, M1, M2, M3. Done. For this one, keep in mind, that's why sometimes if you don't attend the lab, you are losing something or missing something. So for this one, like I said, even though you have a P active covers the whole area, however, the poly is being deposited onto the top of the wafer or into the layer first. So what's going to happen is definitely Fox will be open up, right? So you don't have Fox here. Let's just ignore Fox. So eventually there is a N-well. N-well covers the whole thing. So let's just draw N-well. Okay? And you have P plus. Make sure it's P plus, not N plus, it's P plus. So as you're wondering why P plus is disconnected in the middle, why there's nothing in the middle? Seems like you have a full square here covers P plus, right? P active. Why you don't have P plus in the middle? Because poly was deployed here first, and then it does all the deposition and diffusion. So this whole wafer is being put into the vacuum and have a high pressure, high temperature, or whatever, and have all the P plus material in the vacuum, and it's gonna start diffusing to the wafer. But eventually, this polysilicon is on the top, blocking that P plus and preventing that from being diffused into the wafer. So eventually, that's why P plus here is getting disconnected. There's no P plus in the middle, and that's the whole point making a transistor, because you do need a channel in the middle. So that's the channel of the PMOS. All right, you have the poly here first. That's why there's nothing underneath it. So another question is, why do you want to put poly here first? Why don't we just block it using a different material, and then do this, and then put a poly here? Because in the nano range, it's very difficult to control the precision. Okay, but by doing this, you got a poly here first, and then you do the deposition. Eventually, it's exactly having this P plus material at the edge of the poly, so you don't have to do another step of alignment, which won't happen actually, because these are for the small technologies are in fact like 5 nanometer ranges. How could you align them perfectly? So if you do the poly first and then do the deposition, it's basically doing a self-alignment, right? You don't have to align it for the next step. It's already aligned. Okay? Then what's on the top of it? That's the polysilicon, right? And then metal 1. So for metal 1, there's a via. You can see there's the via. Metal 1, metal 2, metal 3. Okay, that's the answer of this question. Any question from you guys? For question 1, 2, 3? Anything? You're good? Curves. That should be the easy one. Almost 2 curves. I'll do this really quickly, okay? VGS, IDS, boom. VTHN. VDS, IDS, VDS, set. PMOS. VGS, IDS, oh sorry, VSG, ISD, VTHP, VSD, ISD, VSD set. And for the regions, that's saturation. And that's linear region. Why it's linear? You can tell it's linear, almost. And then here's a cutoff region here. Cutoff region happens when you have a really low VGS for the NMOS and VSG for the PMOS. So these are different VGS, right? And x-axis is VDS, and this is the IDS, the channel current and the channel potential drop. And these are different levels of VGS. So we have the VGS which is really low, and the transistor will be operated in the cutoff region. Why? Because VGS is the gate to source voltage. Why it's called gate? The gate controls the current. It's like a switch. You turn it on, then it's going to operate in the on region. If turn it off, it's going to be the cutoff region. That's the whole point of the VGS. And that's why it's called gate. For this one, you could either use the given logic, and eventually you can have A or BC. So A, B, C, these two blocks should be in series. Is the NOR logic, and eventually in parallel with D. Right? For the NMOSes, always think about the NOR gate structure. NOR gate structure have PMOS is in series on the top and NMOS is in parallel at the bottom. So in that case, these two are in parallel, right? In parallel. And also think about the NAND gate structure of the NMOS, and for the NAND logic, they are in series. But usually, remember, based on our experience, we wanted the single transistor on the top. So we should have a D first, and A, B, C are in parallel, and B and C are in series. That's the first solution. You got five nodes, 4 transistors and 5 nodes. All right. So how do we plan for the SIG diagram, the layout? So we have 2 branches of the parallel circuits, and one we need a A here first, and with the D. So we can actually do the D first, because whenever you are dealing with NMOSes, you have to deal with D first. So in that case, if we introduce the wire here and split into 2 branches, so we can name this as D. Okay, this could be D, and then don't rush to make the connection first, because A and D are not shorted. The output of the A and D are not shorted. So you're not supposed to do this. Okay? But however, if this is D, this must be A. Okay, this must be A. If this is the A's output has 2 parallel transistors, so I can do this. And eventually this is the B and C's output, and I can make a connection like this because they are physically shorted. Okay? For here, because I want this to be D, this to be A, so the output over here should connect to D first. So I prefer this to be D. Okay? Wait. This to be D. All right? And then D's output goes to 2 parallel branches. 2 parallel branches. So I can do this, and has to be A first. A, the single one here, the single one transistor branch. So this should be A because this is the A. Okay? And this is B and C. That doesn't matter. Wait, does it matter? Does it matter? It matters, right? Are you getting that? Does this matter B and C? No, because they're in parallel. But now it matters because these matters, so B has to be this one. So they're not getting tangled. Does that make sense? Are we done with the stick diagram of this guy? Any other wires are needed? I don't think so. So, but usually if I see a logic like this, I wouldn't do it this way. I will just combine them first. So I would convert it to AD or BCD first, and we'll make things a lot easier. Now you can see AD are, think about the NAND gate structure. So the PMOSes are in parallel. So need a A and D in parallel and BCD in series. AD, BCD. All right, for the bottom it will be even easier because it's just the NAND gates, two branches in parallel, right? Because the schematic is actually way more straightforward compared to the first version. And it will be the same for the layout as well. 1, 2, 3, 4, 5, 6. Because I have 5 transistors in the 6 nodes. Okay, so the layout will be a lot easier than the first one as well. So first you got 2 in parallel, and then 3 in parallel. We remember that structure, 3 in parallel. Okay, and for the NMOSes, it's even easier. Just 2 branches, and done. AD doesn't matter which is which, but now it matters because this is in series. So this has to be A, this has to be D. If you don't follow that, you are not passing NCC in your layout. So in that case, this has to be A and D. Same for these ones. They have to be B, C, D. Cannot change it because they're in series. The D is the one close to the ground. And then BCD in parallel doesn't really matter. BCD here doesn't really matter. But now it matters because the NMOS has a certain order here. So we are naming them as B, C, and D. And now it's done. Okay? For problem number 6, this one I'm giving students credits if you are calculating a resistance as 160 ohms. Because I didn't tell you where to probe it. For example, you drew a resistor like N well like this. And you are telling me, I want to probe like this. So the resistance between these two, I run current through the 2 nodes like this, is going to be 160 ohms. I tell you like this is 300 nanometers by 1.5 micrometers, but I didn't tell you which is width, which is length, right? Where to probe it. So I also give you credits if you are calculating at 160 ohms. But eventually, my intention was like this. Right? Okay, so these are little squares. So these, if you probe it like this, which means you are putting all these little squares in parallel, right? So these are 800 ohms resistors in parallel. And eventually you can reduce the resistance, right? So if you need a different resistance, you need a resistance lower than 800 ohms, which is a square sheet resistance, right? You need a lower resistance, you have to put them in parallel and you have to probe it like this. However, usually I meant it's the bigger dimension is the width, so this becomes 1.5 micrometer, which is 1500 nanometers. And so you are having 800 ohms per square times 1500 nanometer divided by, for the first one, okay, 300 nanometers, and you're getting 4 kilo ohms for the first one, and the second one is the same thing. So it's just a different dimension, the same ratio, and eventually you're getting the same resistance. Okay, any questions on this? Any question on this? This. All right, can we move forward? So in the final exam, it will be the first half will be the same set of problem like this, right? Because this is the first half of the semester, and second half will be the new materials for the second half of the semester. But so you need to make sure that you can get 100 points on this one in order to perform in the finals. For this one, the equation to calculate the resolution is just like this: 10 volts divided by 1.5 millivolts. That's the ratio of the full range divided by the smallest voltage can resolve. And if you convert it to the digital domain, it will be 2 to the x will be the total number of steps divided by 1. So 1 ISB. So x equals log 2. This number is 6.67, something like this. Eventually, you are getting 12.07, I guess. So eventually, you need 13 bits. Okay, and this one, pay attention to it. I think I gave you guys partial credits if you plot the curve in a reasonable way. Even though you flip them, oh, you flip them 20 points. If you flip them, you're screwed. I still give you partial credits because you know, at least you know how that output curves looks like, right? So if I'm doing this problem, I would label the 2.5 volts first. 2.5 volts which is the middle switching point, and I'm going to draw a line here first. And you know that some of the students are not drawing the output to 5 volts is like 0.5 volts to like 1 volts. It doesn't make sense. The inverter is going to put it up and down to reals, right? It's going to be real to real swing, but there will be a little loss, like 0. 0 point something volts for the PMOS and NMOS, but it will be able to very close to 5 volts, right? Very close to 5 volts. It will be like this. So loss is tiny. It won't be like 0.9 volts or 1 volt for the loss, because remember PMOS is good at pulling the voltage to VDD, right? So which means we're assuming it is able to pull it up to 5 volts. That's the whole point of the logic, right? It's the whole point of the logic. You don't want to use some of the gates are eventually giving you 5 volts logic, but eventually giving you like 0.3 volts logic. That doesn't make sense. If it's a 5 volts logic, you are going to oscillate all the signals at 5 volts or 0 volts. So it should be 5 volts. Okay, that's the middle one. So in that case, if WP over WN is larger, means what? If you compare this VL and V1, these two different inverters. So one WP over WN is 2, another one is WP over WN is 4, and the middle one, what I told you here is 3. Okay, so this is WP over WN is 3, and they all have the same length. That's the principle of the digital circuit design. We always want to use the same length, and which is the smallest length you can use for digital circuits. And that's the whole point why we are changing from like 100 nanometers technology to 95 to 48 to 28, 22 to 10 to 7 to 5 and now to 3, right? Because we want to use the smallest length. To define the dimension of the transistor, and then we change the ratio by varying the width only, but not both at the same time. Otherwise, it doesn't make sense to reduce it to small, decrease the size down to 3 nanometers from 180 nanometers, and the cost is probably 1,000 times more. We just want everything to be smaller and faster, and that's the whole point. So we're gonna use it. If we have the smallest length available, and we're gonna use it. So that's why we keep the length the same and only vary the width. Okay, so the PMOS over NMOS width is 2 to 1, and the PMOS over NMOS is 4 to 1. If I have a larger WP over WN means what? A larger PMOS, right? Because I mean, just stronger PMOS. So stronger PMOS means what? It will be able to hold at 5 volts for longer. So that means it's going to hold at voltage high for longer. I know it's not time, but for more input changes. So if you have a weaker PMOS means a stronger NMOS. Stronger NMOS will hold the 0 state for longer until it cannot hold it. Okay, we'll switch to 1. So that's the whole point. So this is WP over WN, which is 4 to 1. It's WP over WN, which is 2 to 1. Right, so WP over WN, 3 to 1. Okay, if you drew the curves reasonably, I'm still giving you partial credits, even though you flip them. If you are not drawing to real, like to 4.5, 4, and 1, I'm also giving you partial credits. Okay, any question on this? Good. Now let's revisit that SAR algorithm really quick. I'll just give you an example. Okay, give you an example here. Analog signal in. First, you need a sample and hold circuit, and then you need a comparator, and you need a SAR logic, SAR block. That's probably the device covers the most area, and then you need a DAC. So let's say it's a 4-bit, and you need a DAC to convert all the either final results, beginning results, or intermediate results, doesn't matter. Any digital signal appear here will be converted to an analog version of it, and eventually being fed back to the comparator. So given that the comparator's open loop gain is AOL, so V out equals, that's VP, V positive, V negative, VP minus VN times what? AOL. Even though there's no feedback, but does it have a power supply? Of course. In the power supply, right? So the power supply is real to real, and let's say it's 5 volts. So eventually, if VP is a little bit larger than VN because AOL is huge, so AOL ideally is infinite. So that is why if VP is a little bit larger than VN, it's going to saturate the VL to 5 volts, since you don't have 1,000,000 volts available. And whenever VP is a bit smaller than VN, and it's directly saturated to ground, okay, because you don't have a negative voltage supplied. And that's why the comparator is going to output a digital signal oscillating in between 1 and 0s to show you that which one is larger, So in that case, do you need a larger gain or smaller gain? So which one's better? Definitely larger gain is better, right? So it's more sensitive. If a larger gain here, it will be more sensitive. Whenever it's a little bit larger than VN, it will directly saturate, okay? Which is good. You do need that. So for a 4-bit ADC, like this, and let's say it's a 10 volts VDD or 10 volts range or VREF. And now let's convert a 2.6 volts input to its corresponding digital output. Keep in mind, it will be a very similar problem on the minus quiz. And we don't have a homework assignments for you guys, so review this one after this lecture, okay, to prepare for the quiz on Monday. What's the first step? So we want to design the circuit which is able to give you an initial value here. It just reset everything to give you a 1 zeros, right? So that's the first state, which is 5 volts. It's 50% of the range, 5 volts. So remember, sample and hold voltage is going to hold it at 6.2 volts because that's a signal. Okay, and the first reset value here as an initial state given to the SAR, which is 1000, and it's 5 volts. You're getting 5 volts here. So we call this VDAC, and we call this Vin. So if you compare these two signals, you can tell Vin is larger than VDAC, right? And Vin is shorter to Vp. So in that case, we're getting a 1 or getting a 0 as the output of the comparator. 1 or 0 as the output of the comparator. 1, right? It's going to be a 1 as the output of the comparator. So in that case, what this block is going to do is shift all the existing all the codes to the right by 1 bit, including this little one here, and plug in that. Let's call it A3. Okay, so since you eventually are having 4 comparator outputs, I will just call it A3. Okay, so A3, it's going to be a 1, right? 1. And this is A3. So this is 10 over 2 to the 4th times 12. Right? $7.5. Vin or VDAC is larger. VDAC. So V is smaller than VDAC. Okay? V is smaller than VDAC. And then you need to plug in a 0. Plug in 0 there. And this one will be kept in the location and not unchanged. Okay? And it's going to be a 0. 1, 0. It's A3. This is A2. So this is 10. So that's going to be 2.65 volts, 6.25 volts. So Vin is what? Vin is 6.2, and VDAC is this. So this is still smaller than VDAC. So we're expecting what? 1, 0, 0, 1. Okay, this is A3, A2, A1 for these bits. And for the last state, now Vin becomes larger than VDAC again. So we're going to keep that 1, and this one is shifted out. It's shifted out. It's gone. And keep these codes, and eventually this is A3, A2, A1, A0. These are all the comparator's output to form this final SAR ADC's output. And what is this? 5.625 volts. That's the best you can do, even though your input is 6.2 volts, but you cannot reach anything closer to it. Maybe. So what if 1, 1, 1 0 1 0 is going to be this. So this is actually closer, but eventually you are adopting this guy. Is that correct? Should we do that? Seems like this is way more closer to this, right? But algorithm is a lot of times is not perfect. It's getting errors. But let's see if we are making this correct first. So 5. We shift add a 1 because V is larger than 5. So we add a 1, no problem here, times 12, 7.5. Yeah, I think this is right. And then 7.5 is larger, so we are getting a 0. So plugging a 0, and this is 10, which is this guy. And this guy is larger than it. So it's also a 0. It's also 0. Okay, and eventually it's a 1. Yeah, that's how that works. So if you want to make it more precise, you just need to increase the resolution, number of bits for the ADC to make it more precise. But this is the best we can do. Can I do this on Monday during the quiz? Just make sure you understand what's going on here. So as upcoming assignments will be the SAR block. If you look at the whole diagram, it will be this guy. So there will be 2 different blocks of the SAR box, and the first one is called a sequencer. Sorry, it's a code register. Code register. Code register. Because there are 4 bits, so we need 5 D flip-flops. 5 D flip-flops. DQ. That's a physical wire from the comparator's output. Keep in mind, this bit here, exactly this bit. Comp. That's a set pin. And first, it give a 1 0 zeros. So these are the outputs: A3, A2, A1, A0. And let's see if this is true, right? So first, we have a circuit on the top. We don't have it yet, but now we know that this is set it. It's gonna set it, so we are getting a 1 here first. And because these are nothing happened yet, so these are all zeros at the very beginning. Right? Because all the following ones are, the Qs are used as a clock for the previous one. So eventually, when I shift this 1 here, and this one will be set, which means Q become 1 from 0. Okay, 1 will be shifted here, and this 1 will form a rising edge and latch that comparator's output to Q. And here's one question we didn't cover last time. Let's think about this really quick. Okay? So at the third step, as what we are doing here, this one will be shifted here, okay? It's given since we have a circuit on the top to do it. It's given. So all the zeros are filling in the 2 positions here, and this one will be shifted here. And this one will be set. So Q becomes 1, right? Q becomes 1. So look at Q. All right? I can see a rising edge is going to happen as this flip-flop. So you can see comparator's output is shorted to O equivalently to all the D's of the D flip-flops. It's shorted. So which one will receive the comparator's output at this step? The second one, because there's a rising edge. Boom. Okay? So this one will be latched to this Q. Eventually you are getting A2 here. Okay? So my question is for you guys, what if this A2 is a 1? Are you giving a rising edge to this one and then convert this back to A2 instead of A3? But however, if you look at the structure here, we do expect A3 remain at MSB. So what if this one, right, whenever I'm latching the A2 into this bit, if A2 is a 1, what's going to happen to this guy? If this is a rising edge, then the A2 at this moment will be latched to the MSB, and A3 becomes A2, not A3 anymore. Are you guys getting me? So what if A2 is a 1? Because the following ones are getting a 1, it seems like it's giving a rising edge to the previous one. But is this the case here? Why? It's not getting set. But A2 can be a 1, right? So what if A2 is a 0? 0 doesn't matter. 0, there's no falling edge. Or 0 is a falling edge, right? Why is the falling edge? It's the key point. The key point is what? Where to look at. This is the one to look at. If A2 is the 1, it's actually transitioning from 1 to 1. Is it a rising edge? From 1 to 1, is it a rising edge? No. That is important. Why we need an edge trigger flip-flop. You don't want a level trigger flip-flop. You only want everything to happen at the edge. So only samples the data and latch it to Q at the edge. See how clever this design is? Even though this is a 1, it doesn't matter because previously it was a 1, so there's no edge. So what's going to happen to this guy? If there's no edge, what's going to happen? Remain the same. It's memory. That's why it's called latch. So what's the value here? A3. Anything here got changed? Here got anything changed here or no? Yes, it's getting set. That's the whole point. We're shifting this one to the right. Remember this initial one? It's being shifted to the right. It's supposed to go to the right. What about the next? The next one is will be shifted to here. I'm going to ask you another question following this step. All right. So one arrives at this one. Okay. I still have space. So this will be set. It's a rising edge. It's a rising edge. So this guy's going to latch what? A1 to it, which is the new comparator's output, and these ones will remain the same. Why? Because there's no rising edge. Okay, and keep going. Eventually you are getting A3, A2, A1, A0. Why do we need the fifth one? Why do we need a fifth one? For A0, yes. For A0 is what? Clock, right? Because A0 need a following one to provide a clock, a rising edge to it. Okay, so we need a fifth. We need a 5 D flip-flops over here, and they have to be what? They have to be rising edge triggered, and they have to be what? Like set and reset. Cannot be a SR latch without set and reset. You have to set and reset it. Okay. Let's do this really quick. So these are providing all the 5 data lines to the code register like this. Okay, and why this works? Because on the top here's a reset. Here's a set, and here's reset, right? Here's reset. I'm connecting set to the reset over here. And why that works? Because at the very beginning, I'm gonna give a 1 here, give a 1. So this D flip-flop will be set. I'm getting a 1 here. But however, this set pin is shorted to the reset of the following registers, and so the following ones are getting zeros, right? It's getting reset. So that is why we are having this code at the very beginning. And this structure on the top is called the sequencer. So the sequencer, and the bottom one here is called the code register. So the problem is, okay, so the first state is, which is fine because I can do a 1 and zeros, no problem. But so what about these following ones? How do you plug zeros in front of it? How do you plug zeros in front of it? So you need a cycle. You need a cycle to set it and reset the rest. But after that, you want to release it. You give a 0, so all the D flip-flops are not being set or reset. They are being operated in the normal region or normal operation. And then the clocks will work. And then you just short this to ground. So these are all synchronized clocks. Happen at the same time. It's a shift register. So after the first cycle of set and reset, you use the normal clock. It's going to keep pumping zeros to the right because you short the first D to 0. So eventually you are plugging zeros in front of it. But this one is not being changed because this one, the first one, is being shifted to the next one during every clock cycle. Does that make sense? So now you know why this is so important. Why is it so important? And why it's not giving a 0 at the very beginning. Very last question, I promise you guys. Why this 0 is not being sent or not latched to the first one? There's nobody here is switching it back and forth, right? It's permanently shorted to ground. So why is this not being latched to ground? It's a D flip-flop sending D to Q. Why is it not being reset or being latched to ground? Because I set it at the very first cycle, right? I set it. So when you set it, nothing works. So no D will go to Q. Or nothing from D will go to Q. Eventually it's being set. But eventually after I release it, it becomes a normal D flip-flop. So this 0 will be shifted to the right every time. Same to the 1 over here. It's a beautiful circuit. That's why we deserve like 2 quizzes. Just kidding. There'll be 1 quiz on Monday, okay? I'll see you guys on Monday.